In this video tutorial, we're going to be talking about the issue of serial correlation in time series regression models and how we can correct for it. Well, firstly, test for it using the Durbin-Watson test and then correct for it using the Cochrane-Orcutt remedy. So the data set that we're going to be working with is a data set, a finance data set with the S&P 500 index and the price of oil on particular dates from 2015 to just after October 2016. And what we're going to be doing is we're going to be analyzing this data set to see is there a relationship between movements in the price of oil and movements in the S&P 500. And once we run the linear regression, we then want to test for serial correlation with the Durbin-Watson test and then correct for it with the Cochrane-Orcutt remedy. And for this, the purposes of this lesson, we're not going to be using Granger causality, so we're going to be assuming that it's a completely linear model and that we have our two variables at the same time period, the purposes being to illustrate how we would correct it for serial correlation. So basically what we do first of all is when we run our regression model, so we've seen that we have our data set of the S&P 500 and oil prices, and then we run our regression model and we come up with the regression output for the oil variable and the movements on the S&P 500. So based on our independent variable, which is just here, we can see an indication that for every unit change in oil prices, so for every dollar change in the oil price, the S&P 500 changes by 6.54 points. So for every $1 increase in the S&P 500 in oil prices, the S&P 500 increases by 6.54 points. Now, when we run this regression model on its own, we haven't tested it for serial correlation. And what serial correlation is it's basically a correlation between each error term and its previous value. Now, this is going to be a problem when it comes to running an ordinary least squares regression, because if we have correlated error terms across different time periods, it means that that's going to skew our results. Our significance tests are not going to be as valid, so we might make a mistake of, say, rejecting a true null hypothesis or accepting a false null hypothesis, for example. So we want to correct this. So just before I get into the serial correlation, there are four main libraries that we're going to be loading here. So the T-series and LM test are the time series libraries that we'll use to test for serial correlation and also stationarity as well. And the egcm library is what we're going to be using to test for co-integration of the two time series. So what we're also going to be doing is seeing if there's a correlation between the movements in oil prices and the S&P 500 index, but we can't do that using just an ordinary correlation measure. So what we're going to be doing is we're going to be seeing are the two time series co-integrated, and the egcm library, which uses the Engle-Granger method, is what we're going to be using to do that. So moving straight on, when we want to test for serial correlation, we need to run what's called the Durbin-Watson test, and that's denoted by dwtest in R. So we run the dwtest on reg 1, which is the linear model that we've established already, the S&P 500 and oil. And when we run our Durbin-Watson test just down here, we see that with a Durbin-Watson statistic of 0.047, our p-value is essentially 0. So what that means is that the alternative hypothesis of serial correlation is significant at the 5% level, and it means that we can conclude we have serial correlation in our model at that significance level. So what we want to do is we want to eliminate the serial correlation. So I'm going to come back to this in a sec, but basically the way that we would use to eliminate serial correlation is to use what's called the Cochrane-Orcutt method. So Orcutt reg 1 is denoting our Cochrane-Orcutt method using using the regression that we've already established. So we're running Orcutt Reg 1, we're getting the summary, which is just down here. And we see that, well, the first thing we see is that the coefficient for the oil variable has changed. So we can see that for every $1 increase in oil, the S&P 500 is projected to go up by 5.73 points. And what we'll notice here as well is that the Durbin-Watson statistic has been transformed by using the Cochrane-Orcutt method. So we originally had a Durbin-Watson statistic, of 0.047. Now we have a transformed statistic of 2.088, and we see that our p-value has risen quite a bit. So it's above 0.05, so we can't reject the null hypothesis of no serial correlation. So now what that means is that basically we don't have enough evidence anymore to conclude that serial correlation is present in our model, and based on the p-value of 0.8393, we take this regression model as meaning that we have corrected for serial correlation. So the Cochrane-Orcutt method is the method that I've described here to correct for serial correlation, but it comes with a caveat because our time series needs to be what's called AR1 in order to be able to run the Cochrane-Orcutt method. So all that AR1 means is that we have a non-stationary series when we take our time series as is on for each respective time period that we have in the time series. But then when we first difference it, in other words, when we get the difference between the time at, say, x and x plus 1, it means that we're transforming it into a stationary series. So what we mean by a stationary series is that it has a constant mean, variance, and autocorrelation. So for instance, if I draw your attention to the graph down here, you can see that we have our time series, but the trend is not constant. So you can see that we have generally an increasing trend over time. Now, if we have a stationary time series, you can see that there's no trend here. You can see that we have a constant mean, variance, and autocorrelation. It's obvious from the graph. Now, the reason that we want a stationary series is because if we want to be able to forecast a time series, we have to have a constant mean and variance to be able to do that. If the mean and variance is always changing, then it means that it's going to be impossible for us to predict the trend. So if we're using a linear model like ordinary least squares, then we're going to want to have a constant mean and variance, a stationary series, to be able to do that. So one way of inspecting for that is by looking at the plot. There are other more formal ways of doing that as well. So if I just look at my code here and see where we include the ACF, yeah. So when we run our ACF plots, so this is our ACF plot for the original regression, and each line here, each line going up, is basically the correlation between each lag. So we have a correlation of 1 at lag 0, a correlation of 0.975 at lag 1, correlation of 0.954 at lag 2, etc. And basically we want to see what happens to the autocorrelation function when we first difference the series. So when we run the regression on our lagged residuals, what actually happens. So once we run the regression, you can see that our lags, the correlation between the lags after 0, have dropped dramatically. So you can see that they're all below this blue line here. So for instance, we have a correlation of 1 at lag 0, but then we have a correlation of minus 0.056 at 1, minus 0.075 at 2. So the correlations are basically near 0. And the formal test that I was talking about to actually test for stationarity, is by using what's called the Dickey-Fuller test or the ADF test. So this is a simplistic example, but when we run the ADF test here, we can see that we have a p-value for the S&P 500 of 0.4174 and a p-value of 0.4986 for oil. So basically what that means is that if our null hypothesis is non-stationarity and our alternative hypothesis is stationarity, then it means we can't reject the null hypothesis of non-stationarity because our p-values are above 0.05, the 5% level of significance. However, when we get the first difference of the S&P 500 and oil prices, we can see that our p-value drops to 0.01, which is less than 0.05, the 5% level of significance. So it means that we accept or rather we can't reject the null hypothesis of, excuse me, sorry, I muddled that up. We do reject the null hypothesis of non-stationarity, and the evidence here concludes that our first differences are stationary when we get the difference for the S&P 500 and for oil. And another test that we can use to run for this, which works in a very similar way, is called the Phillips-Perron test. And essentially it works in the same way in that we are looking for an alternative hypothesis of stationarity. So again, when we run this test on the variables S&P 500 and oil, we get the p-value above 0.05, so we can't reject the null hypothesis. However, we do reject the null hypothesis when we first difference the series, and we get p-values of 0.01. So once we've established that we have a stationary time series, another way of testing the correlation between two time series, which the OLS is one way, but cointegration is another way, and this applies specifically to time series. And the best way to describe cointegration, supposing that we have a drunk person walking with her dog, and the dog is on a leash. Now, there are times when the person and their dog is going to be walking away from each other because the person's drunk, and you know, there's going to be a bit of stumbling about there. But because the dog is on a leash, they're always going to come back together, so they're never going to go off in a random direction. And cointegration works in the same way. So if you have two time series and you're observing how they move, basically the time series may move apart for a time, but they'll always come back together. They're always on a leash, so to speak. So the time series that you have will show more or less a correlation in that they're going to move back together. If a time series, however, is not cointegrated, then what it means is that you're going to see basically a random walk between the two time series. So the two time series don't have any inherent correlation with each other, and they're just going to move of their own accord. Now, the way that we can test whether two time series are cointegrated or not is using what's called the Engle-Granger test, and we load that using the egcm library as I described. So the command we're running here is egcm oil gspc, so we're running the Engle-Granger test on our oil and S&P 500 variables. So when we run that command here, we get the egcm output, and what we're looking for is our t value. So we see here that x and y don't appear to be cointegrated. So when we come up with the Engle-Granger test, we see that our t statistic is at a point where we don't reject the null hypothesis of cointegration, and it means that our two time series are not cointegrated. So basically what we are concluding from this is that the movements between oil prices and the S&P 500 appear to be independent of each other. Now, while we did establish somewhat of a correlation in the OLS output, it was a pretty much a minuscule correlation. If I remember, it was a 5-point movement in the S&P 500 for every $1 increase in oil prices. So based on that, we don't have that much of a significant correlation, and in the egcm output, it's indeed telling us that it doesn't appear to be co-integrated. So really, to summarize, the most important takeaways from this are that firstly, when we're working with a time series, and particularly if we're using OLS, we need to test the model for serial correlation. We do that using the Durbin-Watson test. One way of correcting it is using the Cochrane-Orcutt method, but we need to make sure that our time series is AR1 in order to be able to do that. We want to make sure that we have a stationary time series, so we would test for that using the Dickey-Fuller, the Phillips-Perron test, etc. And we want to make sure that our time series is stationary so that we can actually make quality forecasts out of those time series, because if we don't have a stationary time series, then it becomes much harder to make predictions. And also, if we're looking at the correlation between two time series, the way that we want to test for that is using cointegration, because cointegration allows us to determine whether the correlations that we're actually getting are significant or whether they're simply due to chance, because many times in a time series you will see correlations between two time series, but there's no inherent meaning behind those correlations. They're simply coincidental. So we want to use cointegration to make sure that that our time series, many correlations are actually significant. So that just about wraps it up for this lesson. Hope you've enjoyed it, and feel free to email me or take a further look at this tutorial on my website if you have any questions, and look forward to seeing you again in the next video. Thanks.